In 7.3, we have similar polygons, and our goal with them is to ultimately find missing sides or missing angles when we know that they are similar. And first, we have to determine whether or not they are actually similar. So the first part we need to determine is what's the definition of similar triangles or similar polygons, that is. Two polygons are similar if their vertices can be paired so that the corresponding angles are congruent. If all corresponding angles are congruent, the other piece that needs to be true is that all corresponding sides form the same proportion. So the given information is that ABCDE is similar to, that's this symbol right here, HIJKL. Some of you may remember this from other grades in terms of the similar figures and how they are solved or shown as proportions. So using the definition of similar, what parts can be congruent of those and what parts also form a proportion, even though you may not know what the values of those segments are. Take a second now and determine whether or not the polygons given in numbers 1, 2, and 3 on your worksheet are similar based on the definition we have here. Answers for questions 1, 2, and 3 are that in number 1, the figures are not similar, and the reason is because not all the sides form the same proportion. We know that 2 of the sides are congruent, which would make their proportion 1 to 1, but A, B, and EF are not congruent, and neither are DC and HG, therefore they are not. In numbers 2, we have all the sides to be congruent in terms of their corresponding sides, but unfortunately the corresponding angles wouldn't necessarily be matching if we knew that it was a parallelogram. Opposite sides would have to be congruent, and same side interior would also have to be supplementary. So therefore number 2, because the angles are not congruent, we know that they're not similar. Number 3, however, equiangular triangles and equilateral triangles are similar, and so when we know that RST has all 3 sides to be congruent, and in triangle WUV all the angles are congruent, equiangular triangles are equilateral and vice versa. Therefore, number 3, they are similar triangles. Take a second now and use that information to look at numbers 4, 5, and 6 to determine missing angles. In this example, we have quadrilateral ABCD is similar to quadrilateral, and this is how it's noted: A prime, B prime, C prime, D prime. So the 2 are related and they are similar, and therefore the scale factor is the ratio of the first figure to the second figure. After that, you should be able to form a proportion in order to find the values of X, Y, and Z. From there, you should be able to then determine the ratio of their perimeters based on the values of X, Y, and Z, and also the perimeters that you see in the figures. Hit pause and answer those questions now. Using DC being corresponding to D prime C prime, you could determine that the scale factor is 5 to 3 by simplifying the ratio of 50 to 30. Based on DC and D prime C prime, you could then use corresponding sides with AD being 30 and A prime D prime being the value of X, setting up a proportion and solving to find that X equals 18. Doing the same thing for the corresponding sides of A prime, B prime, and AB, you have Y being 20, and then same for Z being 13.2. Based on that, the ratio of their perimeters is simply the same as the ratio of their side lengths. We'll get into examples of ratios of areas and volumes of figures, but right now, as long as the scale factor of any length of a side would also be the same scale factor of any perimeter of a figure, because we're still talking about a one-dimension length measurement. Hit pause and answer questions 7, 8, and 9 on your sheet now. Another example we see here is that quadrilateral ABCD has points, and we can use this as coordinate geometry. And then points A prime and B prime are given, and our job is to locate points C prime and D prime so that they are similar figures. So not only do we have to determine the lengths of A to B, A prime to B prime, and A to B in order to determine that, but we can also use a coordinate plane instead of actually having to use the distance formula if need be. Here is quadrilateral ABCD, and so A prime B prime will be located right here at -10, -2, and -2, -2. The distance from A prime to B prime is 8. The distance from A to B is 4. Therefore, A prime B prime is double, and therefore we could then double the length of every single point. It wasn't flipped, it wasn't rotated, it wasn't reflected. And so this point, we can prove that this point right here could also be point D prime. And then from there, we could then conclude the slope of up 2 over 1, or sorry, up 2 over 2 as a slope of 1, dc to d prime c prime could be up 4 over 4, and this could then be c prime, creating our quadrilateral as you see there, and they are similar. One final example here, we have 7 statements, and your job is to determine sometimes, always, or never based on whether they are or are not similar. So number 1, could 2 equilateral triangles be similar? Always, sometimes, or never. They are always similar. 2 isosceles triangles, I just gave that one away, are sometimes similar depending on the angle measurements. 2 squares are always similar. Their ratios and angles are always going to have a ratio of 1 to 1, and also the angles will always be 90 degrees. 2 rhombuses, always, sometimes, or never? Sometimes. 2 regular hexagons. The word regular would mean that they have all the same side lengths in one figure, as well as all the same angles. If they're regular, they are always similar. A right triangle and an acute triangle are never similar. And a right triangle and a scalene triangle, depending on the angle measurements, they could sometimes be similar. Finish up now by answering questions 10 through 12 on your sheet. Bring them in with any questions tomorrow.